All right, we're doing Unit 1, Day 9 notes. And again, there are no Day 8 notes, so this is the first notes from since Day 7. Last unit that we will be doing, last section in this unit, the objective is to distinguish between infinite limits and limits at infinity, and then use them to identify asymptotes. So our first examples, so we're going to take a graphical analysis of limits. We've already seen an infinite limit and a limit at infinity. So these two rational functions here, we're going to look at these. So let's first define infinite limits. So an infinite limit is a limit that results in positive infinity or negative infinity. And where x approaches a is a real number. So this example here, we're going to find the limit of the first function as x approaches 2 from the left and 2 from the right. So as I approach 2 from the left, I'm approaching negative infinity. As I approach 2 from the right, I'm approaching positive infinity. So let's fill the... So on our second graph, g of x, let's approach negative 1 from the left and negative 1 from the right. So same thing, as I approach negative 1 from the left, I'm approaching negative infinity, negative 1 from the right, I am approaching positive infinity. So as these limits, one-sided limits, as they approach negative infinity and positive infinity, what does this represent in the graph? This represents a vertical asymptote. And those are infinite limits. So next we're looking at limits at infinity, and a limit at infinity is a limit in which x approaches negative infinity or positive infinity. So let's look at the two examples we have here. So the first example, f of x, as I approach positive infinity, as I keep going towards positive infinity, I'm going to keep getting closer and closer to 2. As I approach negative infinity, once again, I'm going to get closer and closer to positive 2. So for f of x, as x approaches infinity, the limit approaches 2. As x approaches negative infinity, the function approaches 2. Now let's look at g of x. So as x approaches positive infinity, and it's off my screen here a little bit, but we're going to keep getting bigger and bigger and bigger. So we're going to approach positive infinity. And here as x approaches negative infinity, the value of the function is also approaching negative infinity. So hopefully we see on f of x, we have a horizontal asymptote, and then on g of x, we have what's known as a slant asymptote. So for the limits at infinity, for g of x, as we approach infinity, going up the slant asymptote, we're also approaching positive infinity, and as we approach negative infinity, we're approaching negative infinity. What does this represent as I approach positive infinity and negative infinity? It represents the end behavior of the function. Okay, and what does that lead to? That leads to our horizontal asymptote and our slant asymptote. Sorry about my spelling. Again, not at once, they could be separate. And you'll see me sometimes vertical asymptote, I'll just write a VA, horizontal asymptote, HA. I usually don't write SA for slant asymptote, but I could. All right, next page. So these next examples, we've done these before, so we've already seen how to find infinite limits by combining a numerical and an analytical approach. And so for f of x, which is these top two up here, we want to do that, and then we'll do g of x. So let's first do f of x. And the first thing we have to do is factor. Again, we have a one-sided limit, but we see, hey, we can factor the numerator to 2x plus 3 times x plus 2, the denominator to x plus 2 times x minus 2. We can cancel these out. I know when I substitute in 2, it's going to be undefined. And so now I want to find out, well, if it's undefined, and obviously we know it's going to be at a vertical asymptote, let's now see if it's going to be positive infinity or negative infinity. So what I'm going to do is I'm going to use our numerical approach, and I'm going to, as x approaches 2 from the left, I'm going to pick a point that's pretty close to 2, but coming in from the left, that's 1.9. And now I'm just going to find what the signs are. So 2 times a positive number is positive, plus 3 is positive. 1.9 divided by negative, excuse me, 1.9 minus 2 is a negative value. Positive divided by negative is negative. So I know that this limit is going to approach negative infinity. Okay, we're going to do the same thing as we approach 2 from the right for f of x. Let me set it up. So this time we're going to choose 2.1 as they come in from the right, and I already had it simplified over here. So I'm just going to write that down. And I rewrote the x approaches 2 from the right twice, so make sure you change that right there. So now I'm going to pick 2.1. 2 times 2.1 is 4.2, plus 3 is going to be positive. That's really all I need to know. And then 2.1 minus 2 will be positive. Positive divided by a positive is always positive. So the limit as x approaches 2 from the right is going to be positive infinity. Okay, now let's do the same thing for g of x. We're going to factor. That's these next two examples. Okay, so on g of x, I've set these up. I factored out a 2 in the denominator just to help me make it a little bit easier. But so right here, we're trying to approach negative 1 from the right. So I chose negative 0.9. Negative 0.9 squared is positive, minus negative 0.9, and then plus 1. I know the negative 0.9 plus 1 is going to be positive, and then add a positive, that's going to be positive. Negative 0.9 plus 1 is positive times positive 2 is going to be positive. So here, we're going to approach, the limit is going to approach positive infinity. And now as I approach negative 1 from the left, I'm going to choose negative 1.1. Negative 1.1 squared, and then minus 1.1. So negative 1.1 plus 1, these two together will be negative, but then negative 1.1 squared will be positive, and that's going to be bigger than the result of that sum. So the numerator is going to be negative. Here it's going to be negative 1.1 plus 1 will be negative, times 2 will stay negative, and we get a negative value. So that, hey, the limit is going to approach negative infinity. All right, so now graphically, an infinite limit will always yield a vertical asymptote. In pre-calc, we discovered through observation that such a graphical property existed when a factor in the equation would not cancel out in the denominator. From this point forward, this is not a viable justification for the existence of a vertical asymptote. So what we're going to do now is we're going to look at what actually is justification of the existence of a vertical asymptote using limits. So now for justification of the existence of a vertical asymptote using limits, x equals a is a vertical asymptote of f of x, if and only if, that's what the IFF stands for, if and only if the limit of f of x as x approaches a from the left equals plus or minus infinity, or the limit as x approaches a from the right of the function equals plus or minus infinity. So let's take a look at this example at the bottom of page 2. So for the function below, find any vertical asymptotes that exist and then justify your answer using limits. So I've gone and factored this, and we get 2x plus 1 times x plus 3 and x minus 1 times x plus 3. So I want to find out what the limit is. And again, I know that there's going to be a vertical asymptote at 1, but now how do I justify that? So first thing I'm going to do is find the limit of the function as x approaches 1 from the left. So I'm going to pick 0.9, and I have 2 times 0.9 is positive plus 1 is positive. So we get a positive value. And then 0.9 minus 1 will be negative. So hey, this is going to be negative. So this limit equals negative infinity. And since the limit of f of x as x approaches negative 1 is negative infinity, then x equals 1 is a vertical asymptote. And I'll write that down in a second. Let's first go over and check out this one. So now I'll find the limit of the function as x approaches 1 from the right. So let's come back over to our function. Oop, I keep writing f of x and it's h of x. I'm sorry, I'll change that in a second. So this should all be h of x. So what do I get here? I get 2 times 1.1 is positive plus 1 is positive, and then 1.1 minus 1 is positive, so we get positive. So this will be positive infinity. And so since the limit as x approaches 1 from the right is positive infinity, then x equals 1 is a vertical asymptote. So they both prove it. Let me go make some changes here. So it's not about saying that we couldn't cancel out of the denominator. We're using limits to justify the existence of a vertical asymptote. Obviously, the x plus 3 over x plus 3 would go to a whole, but for right now, we're worried about the vertical asymptote. So you can pause that and write that down. Okay, so now we must develop an analytical procedure by which we can find limits at infinity. And summary, a limit at infinity describes the end behavior of a function. Done a lot of end behavior, both this year and last year. So find each of the following limits at infinity. Give an explanation of your reasoning for each. So I'm going to do a quick summary of what we're doing, and then I'll write it out at the end. Okay, so this first one, I have a cubic function, and I'm approaching positive infinity. I know a cubic function with a negative coefficient is going to look something like this. Doesn't have to be exact. So as I approach as I approach positive infinity, the value of the function is going to approach negative infinity. And again, I'll write this out. So what do we have? Again, I'm looking at the right end behavior of a cubic function with a negative leading coefficient. So it's going to fall to the right. Okay, for the second one, we have, well, and we're not sure. We look at it, hey, I have an x, an x, an x, but this first x is being squared. So that ends up being negative x times negative x times x times x. Hey, that's x to the fourth. And that's going to be a quartic function, and the leading coefficient ends up being positive. So I get positive, again, it's going to be positive 1 x to the fourth. Okay, and I'm trying to see as we go the left end behavior as I approach negative infinity. So what's going to happen, and I'll do this down here, doesn't matter what's in the middle, but as I approach negative infinity, this graph is going to rise, or it's going to approach positive infinity. And I'm going to write that out in a second. So again, quartic function, LC's for leading coefficients positive, which again, both negative infinity and positive infinity will approach positive infinity. All right, last one. All right, this last one, I have a rational function, and I have a degree of the numerator is equal to the degree of the denominator, and whenever we get that, we get a horizontal asymptote, which ends up being a ratio of the leading coefficients. So even though the 3 comes first, the leading coefficient is really negative 2, so we end up getting negative 2 over 1, so there's a horizontal asymptote at negative 2, and I'll write this out. But therefore, as I approach positive infinity, I'm going to get closer and closer to that horizontal asymptote. So the limit here equals negative 2, which is the value of the horizontal asymptote. Again, degrees are equal, horizontal asymptote, negative 2 over 1. So as I approach positive infinity, the graph is going to approach that horizontal asymptote, negative 2. Right, and we're going to take a little bit closer look at some of this stuff with the last example. All right, so this third example, uh, limit of 3 minus 2x over x plus 3 as x approaches infinity is going to allow us to keep working on our analytical process by which we find the limits at infinity for all type of rational functions. So let's investigate these two new functions, both graphically and numerically. So what do we have? F of x equals 3 over x, and g of x equals 1 over x squared. All right, and then the question says, what does each of these functions have in common algebraically, and what do they have in common graphically? Well, one thing I look in both of these, the degree of the denominator is bigger. Okay, that's the first thing we see. And then what do I notice graphically is that they both have a horizontal asymptote, and that horizontal asymptote is at, let's see if I can get it here. There we go. Y equals 0. And that's going to be something we've talked about, but that's going to be something we can use going forward. So here's what we just talked about. Algebraically, degree of the numerator is less than the degree of the denominator, and graphically, both of them have a horizontal asymptote at y equals 0. All right, so we should be on the top of page 4. I don't have in the video what's written up there, but let's look at it. In pre-calc, we learned the 3 rules for determining the existence of horizontal asymptotes of rational functions. When a rational function had a horizontal asymptote, the end behavior was always such that as x approaches negative infinity or positive infinity, then the graph of that function approached the horizontal asymptote. So we learned the 3 rules for determining the horizontal asymptote if one existed for rational functions. We're about to use the idea of a limit and calculus to find out why those rules are such as they are. So for each of these functions we have, we're going to divide every term in both the numerator and denominator by the highest power that appears in the denominator. Then evaluate the indicated limit. And does the result of each limit then make sense based on the graph that is pictured? Okay, so let's take a look at that. Okay, so what I notice here is the highest degree in the denominator is x squared, or the highest power of x. So let's divide everything by that. So I have x over x squared plus 2 over x squared all over x squared over x squared plus 5x over x squared plus 6 over x squared. So let's now go through and let's simplify this. So get the limit. X over x squared is 1 over x plus 2 over x squared all over, hey, x squared over x is going to be 1. This is going to be 5 over x plus 6 over x squared. And this was all the limit of that function as x approaches positive infinity. Well, if I take 1 over x and I let x approach infinity, I'm going to have 1 all over a very, very large number. And that's going to, just this alone is going to approach 0. 2 over x squared, hey, that's going to approach 0. 1 is just going to be 1. 5 over x is going to approach 0. And 6 over x squared is going to approach 0. These last two are zeros. And what do I end up with? 0 over 1. And what does that equal to? That's equal to 0. And if we look at the graph here, hey, this rational function gives me a horizontal asymptote at y equals 0. All right, let's do the same thing for number 2. So we're going to divide every term by x squared, which is the highest power of the x in the denominator. And now let's simplify this. Again, dividing by x squared. So to simplify this, we get the limit of the function as x approaches infinity. And here, again, as I simplify, 2x squared over x squared is 2 plus 7 over x plus 6 over x squared. Give myself a little more room here. All over, sorry about that, 1 plus 5 over x plus 6 over x squared. And now as I look at this limit, as x approaches infinity, well, hey, we're just going to substitute in. That's 2. 7 over infinity, that's going to approach 0. 6 over infinity squared is going to approach 0. Again, any number, 6 is a relatively small number, divided by a very, very large number is going to be 0. 1 plus 0 plus 0. Again, that's a 0, not a 6. And let's get that back. All right, where'd you go? There we are. Sorry about that. And that's going to be equal to 2 over 1. So we just found the horizontal asymptote is equal to 2. What did you do? Back then we just said, hey, the leading coefficient, they're the same. Leading coefficient is 2 over 1. What do we do up here? Hey, the degree of the numerator is less than the degree of the denominator, therefore horizontal asymptote is 0. And we're showing you why it works using limits. Okay, let's do the third one. So we're going to divide everything by x. because that's the highest power of x in the denominator. And by taking this limit as x approaches infinity, we're going to now be able to find out where that asymptote comes into play. So let's simplify this. So this is the limit of the function as x approaches positive infinity. Hey, x squared over x is just x. 3x over x is just 3. 2 over x is going to simplify, stay the same. All over x is 1, minus 1 over x. So now I'm taking the limit as x approaches positive infinity. I'm left with x plus 3. As I direct substitute in, this is 0. In the denominator, I get 1 minus, and that's going to go to 0. So I have an asymptote that is equal to x plus 3, and that's known as a slant asymptote. And look, right there, as we go through, has a y-intercept of 3 and a slope positive 1. Okay, and that's our slant asymptote. Oh, and I jumped the gun there. Sorry, I was I was putting in 1 there. So as we approach infinity, as x approaches infinity, sorry, slant asymptote. So as x approaches infinity, the value of this function, this, sorry about that, that is going to be infinity. Infinity plus 3 is infinity. So I'm sorry, this button keeps getting pushed. So as the function, as I get closer and closer to positive infinity, the value of the function is going to keep approaching positive infinity. And it's because of the slant asymptote. Got excited doing the slant asymptote. And what I'm going to do is I'm just going to call that, I'm over 20 minutes already, so let's just call that part 1 of day 9 notes, and we'll finish the rest of this in class. Okay, so make sure you watch that, and I will give you this part from here on out in class. Or I'll make a part 2 of the video. Thanks.